I'd like to thank Boria for inviting me here. It's my great honor to give talks here. So I'd like to talk about 4D, 2D duality discovered by physicists quite recently, and relation with representation theory. So physical theory is very difficult to understand for mathematicians, but it often gives us some interesting mathematical object as invariant or observable. And sometimes give us not only one, but several interesting mathematical objects. And it may look quite different, even if you start with the same theory. But because we start with the same theory, there should be some relation between these two. Well, there should be some duality between them. For example, if we start with three-dimensional n equals to 4 gaze theory, you obtain some algebraic variety as the Higgs branch. And also a Coulomb branch. So these two geometric objects, algebraic varieties, and the duality between them are called 3D mirror symmetry. Or symplectic duality. Because these varieties are in fact symplectic varieties. So today I'm not going to talk about this 3D mirror symmetry, but I'd like to talk about duality arising from 4D n for d n equals to 4 super conformal theories mentioned in Sergei's talk yesterday. So here we have, for example, we have a Higgs branch. Also, which is closely related with the Coulomb branch of 3D theory via 4D, 3D duality, whatever it means. And also we have Coulomb branch that appears in the first day. And also there's some numerical invariant, which is called the Schur index, which is a certain Q series. So these two geometric invariants, and this is just a Q series. And but because they all look quite different, but because we started with the same theory, there should be some relation or dualities between these three. And I'm not going to talk about this duality because I don't know how to formulate this. I don't think anybody knows how to formulate this duality at the moment. So I basically talk about this duality. So let me start with an example. There's some theory obtained from type 3 F theory, whatever it means. And the Higgs branch of this theory is the following variety. So I think this is a very familiar thing to you. And Schur index here is something like this. So just so you can ignore this factor. It's a 1 plus 3 times q times 9q square 90q third dot. And this is in fact some ratio of eta functions. So eta function is of course so now I'd like to explain what kind of relation with these two. And so this one is very familiar. So N is a nilpotent cone. Of SL2. So this is matrix whose determinant is 0, which is the same as a matrix adjoint operator is nilpotent. Or you can say this is a zero locus of the Kashmir element. In G equals to G star. So this is somehow related to SL2. So, and how about this one? This one is also related with SL2. But you have to consider corresponding affine Katsumudi algebra. So this is a affine Katsumudi algebra. It already appeared. So commutation relation is something like this. Plus this is just a trace of xy, and k is central. And so you can obtain eta function, that's, at least the denominator, by considering the following representation. So I take any complex number, and then I consider the following representation, which already appeared in Misha's talk. So it's an induced representation induced from a trivial one-dimensional representation. This parabolic sum of zero. Here gt acts as 0 and k acts as this number k. And as a vector space, this does not depend on the parameter k, and it's isomorphic to. Can you see? Isomorphic to this space, and this is naturally graded. So this is naturally graded, just positively graded by giving a degree of t to be minus 1. So degree of this element is minus m. And this gives a natural grading on here. So you have
just about notation. Where is n in this sum?
Sorry. N. So this one looks like this. So in degree 0, you have only one vector, which we call a vacuum vector. And degree 1, we have this kind of vectors. And degree 2, we have a kind of vector we have. This kind of vector and this kind of vector and this kind of vector. So if you consider the character of this representation by defining the character as this. So this looks like 1 plus 3q plus 9q squared, and it's agree from there. But the second term is unfortunately different. So this is a bit bigger than the series we want, but we can make it smaller by considering a irreducible quotient. So let me consider the simple quotient, the unique, the simple quotient. So this certainly depends on k. so the question is any k which give us this series. And the answer has been known for a long time. So the theorem of Katz and Wakimoto so this is a very special case of a more general statement. But if you take k to be minus 4/3, which is the same as k plus 2 equals 2/3, then character of this irreducible representation in this sense is exactly this series. Up to some factor. And in fact, it's even better if you consider so-called normalized character. In fact, the trace of a normalized character, which is usually defined as a trace of a Sugawara minus this/24 over this representation. So this is exactly this ratio of a eta function. So somehow we saw that these two are both related with SF2. So now question is whether any relation between this representation and nilpotent cone. Yeah. So if you specify this to be the right number.
No, I understand that's about the theorem that if you take this sample charge, then we get this particular series. But the question is, could you somehow guess it from the very beginning that this is the right sample charge?
Yes, physics tell you. That's what. So this physics, that's what I'm going to explain. Okay, so now question is with so this representation of SL2 hat and the nilpotent cone is somehow rated or not. And in fact, you can obtain nilpotent cone from this infinite dimensional representation in the following manner. So you consider so this kind of quotient space. So this is a very big space. It's too big to rate nilpotent cone. So you want to make it smaller. So the way to make it smaller, I consider this quotient space. And then this became much smaller. So this is so this quotient it is spanned by image of just element with only the T inverse involved, because I quotient of out by this space. So you have a surjection from symmetric algebra G to here, which send this kind of monomial to this vector, image of this vector. And this can be regarded as a function on G star. So if you denote by this map phi, then we can consider following a variety. So it can be defined as a zero locus of this kernel of this map. And this sits inside G star by definition, which is JG invariant and conic. Now there's a theorem of Feigin and Markov in 1902. Of course, this is again a special case of more general statement, which states that if K is this number, then this variety for SL2 is exactly the nilpotent cone. Maybe I explain the proof. So this part is not difficult to see, in fact. The locus of this surjection, kernel of this map. Yeah. So this is this is a quotient of some idea. Like K is the kernel of phi, and this is the zero locus.
Is it the same as the kind of, this is general associative variety?
Yeah.
It doesn't coincide with.
So for affine vertex algebra, we assign this as a type associative. Okay. So the proof is not so difficult, at least this part. So let me explain why. So the irreducible. So of course there's a surjection from this induced representation to this simple quotient, and so there's a kernel which depends on. And for this, so there's some singular vector here. So in fact, for this case, it's known that it's not difficult to see that this is generated by a single singular vector. So this is a singular vector. Which is annihilated by positive half of the SL2 hat. And then this induces the exact sequence. So, yeah. So, so if you quotient out, so I consider the following, this quotient functor, which is right exact. We have this exact sequence. And this one by PBW theorem. So the map for the induced module, this you can define this map. And this is isomorphism because of PBW theorem. So this is exactly the function on G star. So this ideal IK is just an image of this map from this quotient space. So we consider the image of a singular vector in. So the image of a singular vector is inside symmetric algebra function on G, and there's an explicit formula for singular vector. Now from there you can find that this is not zero. The image is non-zero. So there's a Markov Feigen-Fuchs formula for the singular vector. And from there, you can find that the image is non-zero. So this one is element of here, but because it comes from singular vector, it's killed by the positive part of SL2. So in the first, it's just a CE. And by constant, this must be some multiplication by, must have this form. So some power of Kashmir times E times L, I mean. So this means that if you have anything from here, it has to be zero of this function. So it's either killed by Kashmir or killed by E. But if this is case, so this means this belongs to the nilpotent cone. And if this is the case, and recall that this is invariant transaction of G. So this means it's killed by any nilpotent element. And because any element of SL2 can be written as a sum of nilpotent elements. So this means that lambda equals to 0. So in any case, lambda has to be inside nilpotent cone. So this part is quite easy to see if you know the theorem of constant. And Feigen-Markov, Markov-Feigen-Fuchs is formula for singular vectors. And the last part to see, this is exactly the nilpotent cone. I just state the following general fact. So the fact is that for any G, for any K, so you can define this variety in the same way. And this variety is 0 if and only if this one is integrable. integral representation as the hat module. And which is the same as k is non-negative integer. And because this number is not a non-negative integer, this gives finishes the proof of the statement. Yeah, so maybe I state for SL2, there's only 3 possibilities for these varieties. So the most generic case we have, there's no induced module is irreducible. So the variety is just this, and the 0 for the integrable case. And the other case, it must be, so the proof works for arbitrary k. If there's any non-trivial submodule, you get a non-trivial singular vector as a non-trivial vector here. And the argument here gives that it must be the nilpotent form. So this happens when k is sort of admissible or critical. So admissible means k plus 2 equals to p over q, and p, q greater than 2, and p and q are mutually prime. So for SL2, we know what is this variety, but it's in general it's wide open to determine this variety. So anyway, I explained that I already erased, but this Schur index and Higgs branch are connected via representation of affine Katsumudi algebra. So now the question is whether this is coincidence or not. Yeah, yeah.
So this is a little bit more than critical.
Yeah. It's a so shifted debris is positively rational. It just means, so this case is just this is shifted level is positive, rational positive. For other cases, it's irreducible. The induced module is irreducible. Also. So this one is the same as this one if shifted level is not positive rational.
It's not.
If it's positive rational, if integer, then it's integrable.
Okay.
Otherwise, it's either critical or admissible. I didn't define what is admissible.
But -4 because
sorry.
is better than critical. Critical you have the same character.
Hmm?
In a critical level, we can cook up the same character.
Yeah, yeah,
Yes, we can.
yeah.
And all other rational P over Q
I
give the same singular support, but it will be non-reduced. Yes?
So I stated the wrong statement. How do I say? So if k plus 2 is of this form, this is this case. I have to exclude this case. Inverse of integer.
Sorry, but Peter's theorem about computation of the character, it was specific for this minus 4 over 3, right?
Yeah.
So somehow there's only one value of k, which is good for you.
Yeah.
And so I'm confused but they're saying that the variety is equal to n for many different values.
Yes. Because 6 branch have less information than. Okay, so now I'd like to explain about 4D, 2D duality. Due to these people. So what's the day? So many. So maybe I just say BAO from now on. So they constructed a map with certain a functor in some sense from the set of 4D n equals 2 super conformal field series to two-dimensional chiral CFTs. So they reduced dimension by 2. So it's a dimension reduction that Sergei was talking about yesterday. And this is the same as VOA is. So we have a map from 4-dimensional theory to VOEs. And the reason they constructed this is basically the following reason. The Schur index which was the Q series I was talking about of this theory, exactly the character of the corresponding VOEs. So this is nice because as far as I understand, here Hilbert space is not the irreducible representation of a large algebra. You define as a direct infinite sum of a finite dimensional representation. But here Hilbert space is a reducible representation, big algebra, which is just the corresponding VOA. So you can use representation theory of VOA to compute this Schur index. And there's also some properties, other properties. The other properties, the central charge of this VOA, which I denote by C sub 2D, equals the minus 12 of one of the central charge of 4D theory. So this gives a constraint of the central charge of the corresponding VOA. But what I should remark that the central charge should have positive value for unitary theory.
For the series into some concept of central charge.
Yeah. There's a notion of central charge here, C and A, as if I understand correctly. It's something. It's some number. And this some number is positive if you start with the unitary theory.
And your previous example is some specific for this theory. We give this as a 2 minus.
Yeah. For that case, if you compute, so what I want to say is, if you start with unitary theory, you get a negative central charge, which means VOA here it can be never unitary. So this is non-unitary. It's always non-unitary.
And surely this is something what you can calculate. This is something that
Yeah.
just count the dimensions.
Yeah. Some phrase. Some. Now, what I want to give you more example. So I said something like a type 3. And there are some other types for this series. So I'm not going to explain what they are, but the label is 3. That's what I explained. And also 4 and I0 star and IV 4 star and 3 star and 2 star. And corresponding VOA.
So what is this? Just name of series?
Yeah, actually this is Kodaila's labeling of elliptic singularity. It's just a label. So there's 6 cases of this. And all of these VOAs have this form. LKX, where X is the following. So if you want to connect with elliptic fibration, this singularity of singular fiber, and K is minus a check over 6 minus 1. And the corresponding Higgs branch. Yeah, so this is a main example of this paper.
Excuse me, what is written here? Vertex operator LKX?
So X is the algebra 1A to D4 67. And at level K equals minus HX over 6 minus 1.
So you mean that all the arrows are LKX?
Yeah.
Where K equals this for H?
Yeah.
At least first line in A1, what we had before.
Yeah, so this is minus 2 over 3 minus 1. No. Is it equals to 4 over 3, right? And this I remember. So this is a negative integer, which makes it more interesting. And this is what? minus 3 over 6 minus 1, so this is minus. Hmm? Yeah, Dinkin diagram.
No, nilpatent, something like nilpatent in the first.
So,
and he'll write you here right now.
and this is all of this minimal nilpotent oblique closure in X. So now the question is.
And the form of Higgins is minus h check over 6.
Yeah, minus h over 6. 6, yes. Minus 1. In all these cases, yes. So now the question is.
And these three, why they're just elliptic singularities?
Yeah. Because if you have elliptic singularity, you can apply F theory to obtain 4D theory. And then you can apply this map. So now the question now is whether this minimal nilpotent oblique closure is obtained from here as in the same way. And the theorem states this is indeed the case. So let X be as above. So X be one of this, and the K is as this. Then the associated variety defined in the same way is exactly the minimal nilpotent oblique closure.
Does it fail for E3, for example?
Yeah, I think it fails. So actually, this is true for Deline. So this can be considered as a series. So it's called Deline exceptional series. So which is A1, A2. G2, D4, F4, E6, E7, and E8. So this can be considered as a series in the sense that the dimension or more general some representation can be written uniformly in terms of H. And here it's also written in terms of H. And the statement is true for any of the sheets.
But for AC, it's just wrong.
Well, I think it's true. But the proof, just the proof is different.
The statement is true.
Let me see. So what is K minus? So K plus H is I'm not sure. So
before the statement, we can realize the minimal order by this way.
So sorry for S3. It's not true. It's not true. Yeah, it's not true. no.
Is there some value of A equations?
Sorry?
Is there some value of A for A3 equations?
Don't think so. You don't get minimal nilpotent orbit closure as associated duality for S3. Okay, so
But in this case, we cannot, but still, from if I take such orbit, can they correspond to something? Some vertex or a orbit which contain A3 or something like that. Because still to symplectic manifold, symplectic orbit is one to correspond something. Or it is something.
For type A, I'm not sure because so maybe I explain proof of the statement because it's based on the very simple observation. So the proof. So there's a description. There's a simple description of defining idea of minimal nilpotent orbit closure for outside type A. So which is following. You consider degree 2 part of symmetric algebra. And you decompose it into irreducible representation G with respect to the adjoint action. So it have this component, which corresponds to E set square V is square, and the trivial representation, which corresponds to a Kashmir, and I denote by other component by W. So it may have several components. And the statement of Gang and Savan. So minimal nilpotent orbit closure is created the Joseph ideal, and the uniqueness statement of Joseph was wrong, and the Gang Savan proved the uniqueness of Joseph ideal by observing the following. So the fact is that this is zero locus of this W. So it might
W is set of quadratic relations.
Set of quadratic relation, yes. So this decomposes in, so this might have several components.
But we have to take all of them.
You have to take all of them. And so each one has a singular vector which generates the representation. And what you want to do is you want to lift this to a fine setting. So what we do is we consider the following.
And for A, K's relation are not quadratic or what?
Sorry?
For A, what is different?
For A, I don't think it's quadratic, right? Maybe cubic. Maybe I'm wrong. I don't really remember.
Anyway, you want to say the best thing that W have
Several components, and you want to lift to here by considering symmetrization map. So this symmetrization map, G module homomorphism. So the image of this map is singular. If and only if theta t kill all of vector, this vector, and this constraint is just a linear in this level. And if you solve it, and for some miracle for this series, you get this funny level. And sometimes you don't have any common solution. But for this case, it works perfectly. And I don't think it works for S3 in the similar. Now, so physicist.
I don't understand much branch, but minimal orbit can appear.
Can appear.
Branch in these cases or in all cases?
For these cases and for this one, for this case it appears, but for this one I'm not sure. The physicists also ask whether any theory which related to G and D4, but you say the.
I don't think it's not present, but
So anyway, so now the physicists believe that the conjecture is that the Higgs branch of the 4D theory is exactly the associated variety of corresponding VOA for any 4D n equals to 2 super conformal field theory. But I haven't defined associated variety for arbitrary or general value. So I stop here and I continue by defining this thing.